Hello, everybody. Today we're going to talk about Chapter 2, Introduction to Conduction, and quickly reviewing what we had so far on conduction. So if you recall, we mentioned conduction is the transport of energy in a medium due to temperature gradient through random atomic or molecular activity mechanism. We also talked about the conduction rate equation, the conduction rate equation that is also known as Fourier's law. And everyone should remember by now that since we said Fourier's law is a logical phenomena and developed from observation, simply assume you have a long cylinder on sides all around it is fully insulated. So these dots, these lines showing insulation, and you have a temperature gradient across this long cylinder. So imagine at one end, area of the surface is A, and temperature of this end is T1. On the other end, same area, temperature T2, and the length of this cylinder is delta X, and this is the X direction. So after observation, scientists developed that the heat transfer along the cylinder, Q sub X, is proportional to area, directly proportional to temperature difference, delta T, which is T2 minus T1, and inversely proportional to the length, delta X, which we need to have a constant from relation make it to an equation. So now we can say Qx is K, lower k stands for thermal conductivity of the material, times area times temperature difference divided by the length of the cylinder. And as you remember, K, it should be lowercase k, is thermal conductivity of the material. And the unit for this is watt per meter Kelvin. Kelvin is uppercase K. Let's talk about thermal properties of matter. Thermal properties of matter. So the transport properties, what is transport property? The transport property provides an indication of the rate at which energy is transferred by diffusion process. Now, one of the thermal properties is called thermal conductivity. Let's look at the details of thermal conductivity. Also, we show it with lowercase k. Thermal conductivity is a measure of materials' ability to transfer thermal energy by conduction. And if you remember from first sessions, we talked about there are two main reasons for thermal conductivity. Number one, we can have thermal conductivity due to migration of free electrons. Migration of free electrons. Also, we can have thermal conductivity, especially in insulation or low conductivity material, through lattice vibration waves. Through lattice vibration waves. Now, if I'm going to show a quick chart on thermal conductivity of material, this. So horizontal axis show the value for K in the unit of watt per meter Kelvin. So this is 1, this is 10, this is 100 watt per meter Kelvin. On this side I have 0.1 and lower thermal conductivity material. So foams are among the low thermal conductivity material. We have plastic, typically below 1. We have liquids, almost in the region of 1 to 10. So that's a range of thermal conductivities. And we go higher, we have alloys. And pure metal, of course, they have really one of the highest thermal conductivity. So that's one of the thermal properties. We call it as thermal conductivity. We have another property which is called thermal diffusion. That we are showing this with alpha, and Alpha, or thermal diffusion, is thermal conductivity divided by density times specific heat capacity, K over rho Cp. So K is thermal conductivity, rho is density, and Cp is specific heat capacity. And what is thermal diffusion? Is a measure of material's ability to respond to change in its thermal environment. Thermal environment. So we got familiar with two thermal properties, thermal conductivity and thermal diffusion. Now, let's take a look at governing equations for 1D and later for 3D heat conduction in solid materials. So let's take a look at governing equations for, let's start first with one-dimensional heat conduction. In one-dimensional heat conduction, we refer to problems that heat is primarily flowing in one main direction. You can ignore other direction either because they're really smaller compared to the main direction, or the problem has a really 1D and other sides are perhaps insulated. So let's take a look at this schematic that we have a solid material, and let's take one thin slice of this material, like a slice of a cake. And I'm gonna show this thin slice here. And let's assume the area of this is A, so area remains same for the thin slice as well as rest of the material. And we are assuming heat is coming in this direction. That's the only direction, by the way, because that's the direction of X. So we show it Q sub X to the thin slice and leaves the thin slice at Qx plus dx. So this distance is x, that's why heat at this point is Q sub x, and the thickness of this slice is delta x. So at this point, Q lives at the location of x plus delta x, because this is delta x, right? And let's assume we have heat generation as well, like we have an electric heater inside our slice, so which generates heat. So Q sub generation or gen equal to volumetric heat times a volume, which is A times dx. That's the volume of the slice. A is the surface area, dx is the thickness of the slice. Now, if I'm going to write the energy balance for the heat across this thin slice, I need to develop a relation for energy conducted, energy conducted in left phase, let me make it more, plus heat generated within element, plus heat generated within element. That should be equal to change in internal energy plus energy conducted out from the right phase, plus energy conducted out from the right phase. So what we said is that first term is energy conducted in the left phase, which is Qx, heat generation within the element, which is Q dot gen, Q sub gen, equal to change in internal energy. What's the change causing the temperature difference for the slice, and then plus energy conducted from the right, it's showed here. So quickly on this, I can say the first term, which was energy in left phase, is nothing but Q sub x, which is from Fourier's law, we know is equal to minus K A del T over del X, right? Second term is heat generation or energy generation. Energy generated within element. That's equal to Q dot times the volume, which the volume of this slice is area cross-sectional times the thickness. So as shown here. Third term is change in internal energy. That means rho C, specific heat capacity, A del T over del time times dx. So change of temperature of the material by time. Rho density C, heat capacity for solid Cp and Cv are the same. A cross-sectional area, so A dx gives us a volume, and del T over del time is variation of temperature with respect to time. And the last term is energy out from right phase. And that's equal to Qx plus delta x or plus dx, which is equal to minus K A del T over del x at the location of x plus dx. Now, if I'm gonna further simplify this one, if I show that I can use Taylor's series expansion to simplify qx plus dx as qx plus the derivative of qx with respect to x dx. Then I can show that qx plus dx can be written in the simplified form of minus a k del t over del x plus del over del x k del t over del x times dx. So that's basically the simplified form for this after using Taylor series expansion. So here we define few parameters that we already introduced, but let's go ahead and write it down. Q dot was energy generated per unit volume. So that dot represents unit volume. And the units then should be watt per meter cubed. Energy per unit volume. C was a specific heat. Specific heat capacity of the material, unit of joule per kilogram Kelvin, and rho, let me do it here, and rho is density, and the unit is kilogram per meter cubed. Put units in bracket. Now, so that I have the governing equation in this one, I know the mathematical relation of each term. Now let's put back each mathematical term back in the main equation and try to develop a simplified governing equation for this case. So for example, in this case, the energy conducting the left face, I'm gonna put minus Ka del T del X instead of this term. So I will have, I'm gonna combining I'll get minus Ka del T over del X for the first term. So I have this one done. Second term was heat generation within the element. That's Q dot A dx. That's Q dot A dx. And that should be equal to change in internal energy, which is this term. So that should be equal to change in internal energy, which is rho Ca del temperature del time. Really, we're showing time with tau rather than t. Times dx. And then the last term is energy conducted from right-hand side, which we started here, simplified it as this equation in the box. So I have minus a, let's see, I have minus a times K del t over del x plus del over del x, k del t over del x dx. So this is what I have so far. I'm gonna divide both sides of this equation by area times dx. So that means that basically this goes, a dx got cancel out, and I have a dx here cancel out because I'm dividing both sides by a dx. Now this term and this section of this term, they cancel out each other. Minus ka del t over del x minus ak del t over del x, they're exactly similar on both sides. So they cancel each other. So if I want to simplify this equation, I have del over del x, k del t over del x, and remember dx and a are cancelled out. So I have del over del x, k del t over del x, and with a negative sign, so I'm gonna bring it to the left-hand side, becomes positive. I'm gonna add it to Q dot, the volumetric heat generation. Remember, A dx are canceled out. That is equal to this term, which is rho C del T del tau. This what we call the governing equation for one-dimensional conduction, which is del over del x, k del t over del x plus volumetric heat generation equal to change in internal energy term, which is rho c del t over del time. Now let's follow the same procedure, same format to develop a governing equation for a 3D conduction heat transfer. Now I'm going to go ahead with governing equation for three-dimensional heat conduction. For a 3D conduction, let's assume a 3D object. Let's assume this cubic shape. And this is my x direction. This is my y direction. This is my z direction. Okay. Now let's assume heat is coming at Q sub x to basically hit this wall and leaving at Qx plus dx. Remember, the thickness of this is dx. Heat comes from bottom, top, Qy leaves at Qy plus dy. The thickness along the y direction is dy, and same thing with qz. It coming from z direction, qz passes dz distance and leaves here at qz plus dz. So if I'm going to develop the governing equation for this case, simply I say the rate of energy into the system from each direction plus rate of energy generated in the system should be equal to rate of energy leaving the system plus rate of energy stored in the system. E dot is stored, and dot shows the rate, means energy, amount of energy per time. So if I'm gonna further expand those terms, energy into the system are Qx plus Qy plus Qz. There are energy into the system, right? So I would say Qx plus Q sub y plus Q sub z, the energy into the system, plus energy generated in the system. Let's call it Q dot gen for now. That should be equal to energy leaving the system, E dot out, or Qx plus dx leaving the system, Qy plus dy leaving the system, Qz plus dz leaving the system. So that becomes x plus dx, y plus dy, z plus dz. And then energy stored in the system is nothing but variation of energy per time. That kind of represent energy stored in the system. So this is for this term. These three terms refer to this. This is this, and these three terms refer to this, right? Now, if I'm gonna follow the further steps we did for 1D conduction, I'm gonna do it really quick. So Qx is minus K dy dz del T over del X. So what is dy dz? Dy dz is the area that Qx is crossing. Qx is normal to this. So since I have the value for A in this case is dz times dy. That gives me this area, right? That Qx is crossing. So this is nothing but area, Ka dt over dx. And similarly, I can write Qx plus dx, remember from Taylor series expansion. I can show it in this form, that minus K del T over del X plus del over del X of K del T over del X times dx, and everything times the area. Again, area is dy dz. I can do the same thing for Qy and Qy plus dy. Qy is minus K dx dz del T around del y. Quickly, Qy is dx dz because we are referring to this area. This is Qy, into this area, and this area length is dx times dz. This is dz. So that's why we get dx dz as our area. And qy quickly plus dy is minus k minus bracket k del t over del y plus del over del y k del t over del y times dy, and everything times the area, which we showed is equal to dx times dz. So that takes care of y direction. We also have qz, which is this, coming into this area. qz is k dx dy del t over del z. So this area is dx dy. And qz plus dz, is equal to minus bracket k del t over del z plus del over del z k del t over del z dz, and everything times dx and dy. I'm going to erase this section. dx dy. dx dy represent our area where qz is crossing. Two more terms to define. I'm going to do it in this slide. So q gen, we used it here. What is this? I can show q gen as equal to volumetric heat generation times area of this little cube, this little element is dx times dy times dz. dx times dy times dz, that gives me my area. So if I multiply this area to volumetric heat generation, that gives me amount of heat generation. And this term, dE over dT, I can show it in the form of rho C volume V, or V I have dx dy dz times variation of temperature with respect to time. So again, similar to 1D direction, 1D dimension, we first defined our governing equation for 3D case. Then we showed the details in mathematical form. So each term has its own mathematical form. Further, we expanded the details of this. So Qx is defined as this. Qx plus dx is defined as this. Same thing for other terms. Now is the time to combine all the mathematical terms back into the main governing equation and trying to cancel out similar terms on both sides of the equation and simplify our governing equation. Now, if I combine those similar to what we did previously, I have, let me go here quickly. For example, I'm gonna replace Qx in energy in, of course, and then replace Qx plus dx in energy out. And you can notice later that this term is exactly repeated here, right? This term and this term, because it's multiplied to the bracket. So they cancel out each other. So we're gonna have several similar terms that are gonna cancel out. So if I do this simplification, I have del over del x, k del t over del x, plus del over del y, k del temperature over del y, plus del over del z, k del t over del z, plus q dot should be equal to rho c del t over del prime. Now this is our governing equation, by the way. So this is our final answer. This is, we call it governing equation in three-dimensional heat conduction. Now, if I'm gonna assume one simple assumptions that works for many cases, that for constant K thermal conductivity, then if K is constant, then K can go outside of the derivative as a constant. And since in several terms we have K, we can somehow divide both sides of the equation by K, and we get a new form, new simplified form of this. And K constants can be true for many materials within the specific range of temperature, that K doesn't vary that much, so you can really assume constant thermal conductivity for materials if there's no huge change in temperature, for example. So if K is constant, I'm going to divide both sides by K, and we'll get this form. Del 2T del x squared plus del 2T del y squared plus del 2T del z squared plus heat generation term doesn't have K, so it's simply divided by K, and I divide rho c over K, so I have rho c over K del T over del time. And remember, earlier we defined thermal diffusion as K over rho c. Thermal diffusion. So this is nothing but 1 over alpha. So this can be written in the form of this as well. The y squared plus 2t del z squared plus generation 10 divided by q is equal to 1 over thermal diffusion alpha del T over del tau. This is my final form of governing equation for 3D heat conduction if K can be assumed constant. So this is for constant K. Nice. So far we talked about Cartesian coordinate system, right? We always talked about, hey, let's talk about x, y, and z direction. Now, what if we're gonna solve our problem in cylindrical or spherical coordinate system? What if the problem is in a way that using cylindrical or a spherical coordinate system makes it much easier to handle the problem? So I'm not going to go through the details of those, but I just want to write down the final form of governing equation for those cases, but the process is the same. So in cylindrical coordinate system, Cylindrical coordinate system, by the way, looks like this. If I take a small element in a cylindrical coordinate system, should looks like this. This is my element. This is dz. This is phi, and this is dr. So this is just the final form. That second derivative of temperature with respect to radius plus 1 over r del T over del r plus 1 over r squared. Second derivative of T with respect to phi squared plus 2t del z squared plus q dot over k. That should be equal to 1 over alpha del T over del time. And same thing for a spherical coordinate system. I just want to quickly show it. Where you have 1 over r, second derivative with respect to r of r t plus 1 over r squared sine of theta del over del theta sine theta del t over del theta plus 1 over r squared sine squared theta times second derivative of t with respect to phi squared plus the heat generation term q dot over k is equal to 1 over alpha del T over del time. So you had R, Z, phi here as a variable. So we just showed the cylindrical and spherical coordinate systems, how the governing equation of conduction heat transfer works over there. Now, let's go back to our simplified version of the governing equation in Cartesian coordinate system. So remember the governing equation and the simple case where k was constant. We said governing equation is equal to in Cartesian coordinate systems second derivative of t with respect to x plus second derivative of t with respect to y plus second derivative of t with respect to z plus heat generation term is equal to 1 over alpha del T over del time. Now, let's look at different conditions that we can cancel out or we can simplify this equation even further. For example, consider a steady state one-dimensional heat flow. heat flow with no heat generation. So it's a steady state, so the transient term should go 0. So let me do this. So a steady state means that boundary conditions or temperature in a steady state after a long time when the solution is achieved remains constant. So they're not changing by time. So this term goes to 0. 1D heat flow, so let's take care of this. 1D heat flow basically means that you can assume one direction only and there's no heat transfer in other direction. For example, if you go with X, then you can say there's no heat transfer in other direction. So those goes to 0. And no heat generation means that Q dot is 0. So our equation really simplifies to just the first term, right? Second derivative of t with respect to x equal to 0 for this case. Now let's take a look at another example. Let's assume a steady state, one-dimensional heat flow with heat source, with heat generation. What happens here? So let's do the same thing. I'm gonna erase those and say, okay, you have a steady state. So the transient term goes to 0. We have 1D heat flow. Let's assume it's along the x. This and this goes to 0. And we're gonna keep the heat source because this time we have a heat source. So the only two terms remain are second derivative of t with respect to x plus q dot over k. That should be equal to 0. Let's do one more case before we go to next part. Let's assume we have two-dimensional steady state conduction without heat generation. Without heat generation. In this case, I'm gonna go ahead, erase those. So I have a 2-dimensional. Let's assume that's along x and y, so z goes to 0. A steady state, so transient term goes to 0. Without heat generation, so no heat generation, this goes to 0. So my simplified answer is first two terms only. So I'm going to have second derivative of t with respect to x plus second derivative of t with respect to y equals 0. So that's how we further simplify the main governing equation. Now, one last part, and that's end of today's session. We're going to talk about boundary conditions and initial conditions. So let's talk about boundary conditions first. So whenever we solve a governing equation in a field, in a region, we need to bound it so we can find a unique solution for that governing equation or that partial differential equation, right? So we need to know what are the boundaries value. In some cases, we need to know what are the initial values. So boundary conditions, there are different types of boundary condition. Type 1 is constant surface temperature. That's where we know what is exactly the temperature of the surface at the particular location. If T of 0 and T is known, for example, if this is a wall, and we know that temperature on this wall is Ts and changes by time, so we know the exact value for the temperature on this certain boundary. That's called constant surface temperature. And this is also known as Dirichlet condition. Also, it's known as boundary condition of the first kind. Okay. Number 2 is where we know the constant surface heat flux. That we can divide it into 2 sections. Section 1 is, let's call it constant surface heat flux. Yeah, constant surface heat flux. The same as what it sounds like, which means that the heat flux is known at the boundary. So minus K del T over del X, that's familiar, that's Fourier's law, right? That's the amount of heat flux to the surface. At a particular location, let's call it x equals 0, is known in that case. So for example, you have a wall and the amount of heat flux to the system is known. So you can apply the constant surface heat flux to the surface. By the way, this is known as Newman boundary condition. Newman condition, also famous for boundary condition of the second kind. And part B of constant surface heat flux is where we have adiabatic or you can also call it insulated surface. That's where our surface is insulated. So if a Q comes in, there's no way for heat to flow into the boundary, so Q is 0 at that surface. So that's, we can show it as del T over del X at a particular location. Let's call it x equals 0. That's equal to 0. We also have convection boundary condition or convective. boundary condition. That's where we have a surface close to a fluid with a known T infinity and heat transfer coefficient. So the temperature varies based on that, and we can show it as minus K del T over del X at a location. That should be equal to H T fluid minus T of the surface at that location. So basically here we're saying that if this is my boundary condition, amount of heat comes in the form of convection, this form, which is H T infinity minus T, should leave the surface in the form of conduction, the solid, right? Which is equal to minus K del T over del X. So we talked about 3 different types of boundary conditions. Now, quickly on initial condition. We can say for transient conduction, so this is needed for transient conduction. For transient conduction, heat equation is first order in time, requiring the specifications of an initial temperature distribution. So we need to know what was the temperature distribution at the initial time, at time equals 0. So we need to know Tx and 0, that's how it looks like. And since heat equation is second order, we need 2 boundary conditions to fulfill and only 1 boundary initial condition for time related value. So this is it. That's the end of this session today. Most of the governing equations we developed are really to understand the process. So when we develop the governing equation for 1D or 3D in Cartesian coordinate systems, and we showed that similar approach can be done for cylindrical and spherical coordinate systems. So we're going to make sure we understand the process. When we see the final governing equation, the simplified, we can follow, we understand how the final equation is derived. That's the whole purpose of this chapter. We also got familiar with thermal properties like K, thermal conductivity, and diffusion, thermal diffusion, alpha. We also studied 3 main boundary conditions and about initial condition as well. Thank you, and you have a great time.